Okay, when we were looking at the Fibonacci function, we saw there were two problems. First of all, the function slowed down significantly as it was running, and the longer it ran, the more it slowed down, and it seemed, in fact, to slow down exponentially. And we looked at the reason for that. We'll get back to that in a second. The second problem was the negative numbers began to appear, which made no sense because Fibonacci is an increasing positive function, right? The numbers are always positive, and the further out you go, the more positive they get, the bigger they get. So we took care of that second problem because we looked at how binary numbers are implemented. We saw there was a problem of overflow. But what about the second problem? What about the issue of how do we handle the problem with these with the numbers, with the function taking longer and longer? Just to remind ourselves what the problem was. So if we were calculating, for example, Fibonacci of 8, so in order to do that, you have to first calculate Fibonacci of 7, and then Fibonacci. When you got back from there, you have to go do Fibonacci of 6, and finally you can get this guy here. What I want to do is trace how many times we're going to actually calculate Fibonacci of 3. So we're going to work our way down here, right? We're going to work our way this way, and then this way, and this way. We can't do any calculations yet. We're simply making calls. And we do Fibonacci of 4. And now we come to Fibonacci of 3. We don't have a value yet because we're going to make 2 more calls on the Fibonacci function. First to get Fibonacci of 2, that's going to give us a 1. And then to get Fibonacci of 1, that's going to give us a 1. We can come back over here and add it together, and that's going to give us a value of Fibonacci of 2. Now what I want you to notice over here, we saw this the last time, was that how many times is this thing going to call? How many times are we going to get Fibonacci of 3 being called? Here, and here, and here, and here, and I'm probably missing some, and here, and over here, right? So that's what's causing all the immense amount of time that it takes over here. Every time we want to calculate something, we end up recalculating it multiple times. I mean, look at Fibonacci of 4. We're going to calculate it over here, and so on. So doing all these calculations multiple times. So an obvious idea how to do it, might have to think a little bit, but the obvious idea is instead of making all these multiple calls for the same value, if every time you got a value, let's say in order to you have to calculate, say, f of 6, well, then you have to do other calls. When you finally get a value, right, like for example we saw this when we get this Fibonacci of 3 over there, so why don't we just write it down, right? In other words, take a piece of paper and write it down. And then when you have to calculate some value, first check to see if you've already calculated that value. And if you had, then just use it instead of making the function call. So if that were the case, let's say we calculated f of 5, right? At one point, we have the value for f of 5, right? So that means with something like, let's say over here, we did f of 5, right? So once we did this, once we calculated f of 5, let's say over here, the next time when we come down over here and we encountered f of 5, instead of doing this whole business, we just look it up someplace, and then instead of going down and doing that calculation, we already have it. So you're saving all this call here. And likewise, when we get to do this one, we simply look it up on the table. We'll see how to do the table in a moment. And then you don't have to do those calculations, right? You save all this stuff. And clearly, the bigger this tree is going to get, the more you're going to save once you write those values down. That's a very clever idea. So just to recap, the idea is once you finally have a value, just write it down, put it in some kind of array or some kind of table, and every time you want to calculate a new Fibonacci number, before you go off and make those calls and all those recursive calls, just check if you've done it already. And if you have, then don't do it again, right? You just don't do it again, and you'll be in good shape. You'll save all those calls. This idea, as simple as it is, it's extremely useful, and you'll see we're going to actually run Fibonacci again when we implement this thing, and the dramatic increase in speed. It's like it'll blow you away. It's overwhelming. Okay, so the idea is very useful, and it has a name, and the name is memoization, right? Memoization. Now, what is it not? It's not memorization, it's memoization, right? Why memoization? Because basically the idea is like, imagine you have a memo, right? You write yourself a memo, and every time you calculate something, when you finally have a value, you just put it in the memo. And then as you're doing a more complex calculation, before you go off and try to do the subproblems, just check to see if you've actually done those subproblems. If you have, then don't do them again. Just use the value and continue in the larger calculation. So what's a memo going to be? Basically, a memo is going to be a table, right? We'll make a one-dimensional array. We can call the one-dimensional array memo, and let's say it looks like this, right? A regular one-dimensional array called memo. So here is memo sub 0, memo sub 1, memo sub 2, right? Memo sub 0, sub 1, sub 2, sub 3, sub 4. We initialize the whole thing to 0, right? And that's easy to do. Why do we initialize it to 0? Well, because no Fibonacci number can be 0, right? At least in our implementation, it's going to be, it'll be, 1 and 1 and then 2 and so on and so forth. And so then what will happen is once we do, and then we might as well do some initializations. We can set, let's say, this memo of 1, which will be, this is going to be our n race, basically. So when n is equal to 1, we know what Fibonacci is going to be. It's going to be 1, and over here it's going to be also 1. So so we'll actually pick up from here, right? And so we're going to put this table into the Fibonacci function that we wrote. And we'll see exactly how this works. It's really such a very cool idea and very, very easy to implement, right? So that's what we're going to look at now, how this thing works. Okay, so here is the Fibonacci function, right? The one we've seen. So we're going to do it slightly differently. We're going to make the memo a little bit different, as you'll see in a moment. But this is the old function that we wrote. We're going to calculate Fibonacci of n. We're going to check if it's 1 or 2. If it is, we're going to return 1 because we decided the Fibonacci of 1 and Fibonacci of 2 are 1. Otherwise, we're going to calculate Fibonacci of n minus 1 and Fibonacci of n minus 2, add them together, and return the value. Right? This we've done, and we're going to try to do this in a loop and do it 100 times. So if I run this thing, as we've done before, let me just remind you about how slow this thing is. Right? It goes fast, and then 41 it slows down, and 42, and 43, and each time it's actually almost twice as fast, twice as slow as it was before. 45, and it's getting slower and slower and slower. So the idea is we're going to write down the values once we calculate them, and instead of having to recalculate those sub-values each time, we're gonna just look them up. So we're going to go into the function right over here. And we're going to create a one-dimensional array, and that array is going to be called memo. So it's going to be an integer array, memo, and let's say it's a size 100, and we're going to initialize the array because we already have the 1 and 2 in here. So we're going to just initialize the array all to 0, and we saw that we can do that earlier in the semester. So now we have an array of size 100 initialized to 0. That's a good way to initialize it because no Fibonacci number is 0. So if we look up, let's say we want to calculate Fibonacci of 17, and we look at memo so 17 and we see it's a 0, that's going to tell us we've never calculated that, because had we calculated, we're going to basically store the value. So once we calculate, say, Fibonacci of 17, we're going to store it there, and memo of 17 will no longer be 0. That's basically the idea. So now what we're going to do is how else do we have to modify this? So if n is equal to 1 or n is equal to 2, then we simply return 1. That's the definition, right? That's why I don't want to do the initialization up here. But now what happens if it's not 1 or 2? Let's say it's 17. So before I call Fibonacci of 16 and Fibonacci of 15, what I'm going to do is just check my memo, right? So if I've already calculated it, so if memo sub n, right? Because that's what I'm going to do here. If memo sub n is in fact greater than 0, right? If memo sub n is greater than 0, what does that mean? That means I've already calculated it. And so I don't want to recalculate the things. I just want to return the value in memo sub n, right? Just return that value. So what's going to happen is, instead of, if I've already calculated memo sub 17, I've stored it here, I'm not going to go down and then calculate again memo a Fibonacci of 16 and Fibonacci of 15. Because once it's stored, I'm going to save myself all this stuff, right? Now, but where do I get the value in memo, right? So let's say I did not, let's say n is 17, and memo sub 17 is not greater than 0. So I'm not going to return the value. I'm going to calculate it over here, right? So once I come back from Fibonacci of 16 plus Fibonacci of 15, that will give me Fibonacci of 17, right? And that's true for any n. If I've not yet stored Fibonacci of n, so that I'm going to calculate it over here. When I come back from this, I will have Fibonacci of n. So all I'm going to do here, before I return it, I'm going to say memo sub n, right? Because that's what I'm calculating now, is going to be equal to Fibonacci of n minus 1, Fibonacci of n minus 2. So when I come here and I'm going to calculate Fibonacci of 17 for the first time, and I'm going to see Fibonacci of 17 is, it's not greater than 0, means I haven't calculated because it's going to still be a 0 in there. I'm going to calculate it and store it. And the next time I come in, right, to calculate Fibonacci of 17, this will no longer be true because it's going to be, this is going to be true, right? Because it's calculated Fibonacci of 17 already. It's not a 0 there, so there is a Fibonacci number in there, so I'm just going to return it and not recalculate. Such a great idea. So now watch this. Watch how fast this thing is actually going to go. I hope I didn't make any mistakes in terms of the syntax. Let's see. Wow. Okay, see. Watch this. Watch this baby run. Watch what's going on here. So much faster than it was, right? So this idea is very, very good, very useful. And you see how slow it was before and how fast it is now compared to the previous case. This is like, you could just watch how fast it is. Everybody see that? We should actually timed it, because then we would see the tremendous increase in speed. Doesn't really look like that much faster. It's supposed to work. Let's just stop this and look at this program. Just take a minute over here. I mean, it's such an important idea and such a famous idea. Why is it not working? Why is it not working? I'd like you to just stop the video and see if you can come up with some kind of answer. It really, really should be working here, right? What's the problem? So let's analyze this together. I mean, it should work. Let's say Fibonacci of 17, right? So I'm going to do Fibonacci. I'm going to come in here and I'm going to write it into my memo. And the next time I come in, it's going to be in this memo. And so why does it not find it? I mean, obviously it's not speeding up, because if it found it, can you see what's going on? Can you see what's going on? Is there any way that I could actually make this work? Why is it not working? So the answer is, I hope you thought about this. The answer is very simple. If you take a look at memo, right, this array of 0, the whole idea is every time we make a new call, we're going to be filling it in, right? That's the whole idea, right? So I have to recalculate the values that I've stored. But the way that I set it up, remember, all these are local variables, right? So memo is also a local variable. So every time I come in, I'm going to get a new value of memo, and it's going to basically wipe out what I had before, because it's not going to be that array anymore. So I need some way to make sure that this memo array doesn't get destroyed between calls. And we've seen how to do that early in the semester. There's a special keyword that I use to say, I want these particular variables to stay between calls. Do you remember what that is? That's something called static. Remember static? So if I put static in here, notice it's a keyword, right? So what's going to happen is this will get initialized only the first time, but every subsequent time, it's going to, remember, this is going to store it someplace else. Remember that diagram we went through a number of times. We said the statics and the consts are stored someplace not on the runtime stack. That's why anything here on the runtime stack, that every time I get a call, that's going to get, every time I come out of a function, what's on the runtime stack disappears. But the static stuff, since it's not on the runtime stack, it's not going to disappear. And so I will be able to have this array last from call to call, and that might work. Right? So let's try and see if it speeds it up. Remember how slow it was, right? It was slow as molasses. Watch what happens now. I'm going to run it. Ha! Look at that. Look how fast it actually went, right? So what's the problem now? The problem is it's fast, but it's still wrong, right? It's fast but wrong. So, okay, at least we solved one problem. Is there any way of obviating this? I mean, but this is a very cool idea. We'll see later on how important this is, because this idea of recursion, when you have these overlapping subproblems, we're going to talk about that in a moment, but things that look like, many problems look like Fibonacci in terms of their structure. And I'll make that clear in a moment. Many very important problems and applications have that characteristic. And so this memoization technique, together with recursion, is used all over the place in optimization problems and so on. Many algorithms that you learn in the algorithm class are going to be based on this topic. It has a name. It's called dynamic programming, and we'll get it in a moment. But so what that did, of course, is solve the speed problem, but it did not solve the negative number problem, right? That still is an issue, right? Okay, so before we go back and talk about dynamic programming in a little bit more detail, and we'll see a lot of it as the semester progresses, I just want to show you this. It's the same function, almost the same program, except it's in Python. So my memo I call M over here, and this gives me an array called the list in Python, which is size 101. So everything is initialized to 0, just as it was over here in the C++ program. Memo sub 1, memo sub 2, they're defined to be 1 as over here. But here I'm making the call. Here I'm going to explicitly put it into the memo. But it's the same thing, right? And here, and I'm assuming, just like over here, that no one's going to ask me for a 0. I'm checking for it explicitly, and if they give me any value less than 1 or greater than 100, I'm simply going to print an error message and say, it's out of range and return. So this doesn't bother me. But what happens, let's say you're going to come in here to do Fibonacci of 17. So if Fibonacci of 17 is greater than 0, right? So let's say it's the same as before, right? If you've never put anything in Fibonacci of 17, it's going to be equal to 0 because the whole memo was initialized to 0, right? But it's only when you finally calculate Fibonacci of 17. By calculating, you made the call, n was equal to 17. M of 17, memo of 17 is not greater than 0 because you didn't calculate it yet. So you're going to calculate Fibonacci of 17, because n is 17, by Fibonacci of 16, get the value back, plus Fibonacci of 15, get the value back, add them together, and then you're going to store it in the memo Fibonacci of 17. And the next time when you need it, so for example, you come in here, let's say Fibonacci of 18. So you're going to ask, is Fibonacci of 18 greater than 0? Well, it's not, right? So you're going to calculate Fibonacci of 17 plus Fibonacci of 16. But when you come into the Fibonacci of 17 calculation, come down here, and it's no longer going to be 0 because you've calculated and stored it. So this whole subtree is not going to get calculated. And if you think through this, the Fibonacci of 16 has been calculated already, so this is going to be super fast, and those whole subtrees are not going to get calculated. So let's see what happens when I actually run this, right? When I run this. I'm going to go over here and say, run this thing, and let's see what happens. Wow. So first of all, it's fast, right? Not quite as fast as the C++ program. I don't know if you really notice this. It's considerably slower, even though it looks fast. But moreover, you'll notice there's no negative numbers over here, and you'll also notice that it's correct. So what's Fibonacci of 100? It's Fibonacci of 98, 99, right? Well, 9 and 6 is 15, right? Carry the 1. That makes it a 6. It makes it a 5 and a 6 and a 7. And this thing really works. So how come they get it right? How come the people that wrote Python, I mean, they're smart people, right? But the people that wrote C++ are also pretty smart. Why did these guys get it right and these guys did not? So the answer is because what's happening over here is that all the arithmetic is simulated, right? It's like the first program you wrote for the semester. the add function, you're doing everything by simulating the addition by using these big integers that are stored in arrays. And so you're doing the arithmetic on not on the real, you're not storing the values of these giant numbers in a memory location, because they can't fit it. The memory location has either 32 bits or 64 bits, but certainly not big enough to fit these giant numbers. So this is going to be, so that's why this thing works. Python is simulating all the arithmetic, while C++ is not. Right? It's doing the arithmetic actually using the memory locations. Does that mean you can't solve this problem in C++? Of course you can, right? But you have to do the same thing as you're doing in Python. You have to use a library, like a big integer library, that simulates the arithmetic as opposed to doing it directly in the memory locations. If you do it there, it's going to be much slower, of course, than stuff that's in the locations themselves. But of course, it's not going to be wrong. It's going to be correct. And so if you need to do that kind of calculations, that's what you would do, right? So it's interesting to see how it works in Python. So this technique of using recursion and some memo where we write down the calculation, the values that we calculate as we're going along, that's called dynamic programming. And just let's make sure we understand where it's applicable, right? It's applicable right over here. Why? Because first of all, we have a situation where the function itself is recursive, right? In other words, to calculate f of 8, so what we needed to do, we want to get f of 8, so we had to calculate first f of 7. So we're calling the same function f it's the same Fibonacci function, right? We're calling it on f of 7 and f of 6. Right? So we have a situation where we have something that's defined recursively. So that's the first characterization of situations where this dynamic programming approach is useful. And second of all, we have these things called overlapping subproblems, right? So what does that mean? It's a fancy term, but the overlapping subproblem, let's say calculating f of 5. So we're calculating f of 5 here, and we're calculating f of 5 here, and we're calculating f of 5 over here. So there are sub-problems we're going to keep doing again and again and again, right? Those are overlapping in terms of the overall calculation. We're going to do them repeatedly. So when we have that situation, namely, we have a recursion and overlapping sub-problems, what we can do is we can take that recursion and we can modify the recursion so it's going to be faster with the memoization, and that's the way we do it. So as we saw, it's called dynamic programming, and the history of the term is over here. It has nothing really to do with programming as we talk about programming today, programming a computer. It's programming like programming television programs. In other words, in the sense that I have to decide when to do something. So I do this first, and I do this second, I do this third. So you do these pre-calculations, and you look those pre-calculations up. This is taken from Wikipedia. It's interesting, a little bit of the history, and we'll see. As I said, we'll see this later on. Now, what's really interesting is in many applications of dynamic programming, there's another way to accomplish the same thing, and so that's going to be very helpful. What do I mean by that? So if you look at what we did, we had a recursion, and then we memoized the recursion. Now, this recursion is a top-down thing. What does it mean, top-down? What does that mean? That means, let's say, for example, if we wanted to calculate, let's say we wanted to calculate f of 7, right? So we started with the number on top, f of 7, and we said in order to do that, first I have to get f of 6, and then I have to get f of 5. And after I get those two things, I can add them together and get f of 7. Right, so I'm working from the top, right, the big number that I wanted, I'm working my way down and then back up again, right? So that's a top-down approach. But if you think about it, what we're really doing with this memoization is, in fact, filling a table up, right? We're filling up the table. We're going to go down, all the way down to the bottom. We get a value for f of 1 and f of 2 if we didn't store it there. And then when we get f of 3, we'll have calculated that. And then we're going to get f of 4, because that's going to be f of 4 is going to be f of 3 plus f of 2. So we'll have f of 4, right? Does that make sense? If you think about it, it's going to look something like this. So if, let's say I want to calculate f of 7, right? This is my memo. So f of 7 here is 0, right? So I'm going to calculate f of 6 plus f of 5. So to get f of 6, I'm going to first calculate f of 5, and f of 4, then f of 3. So to get f of 3, I'm going to add these two. I'm going to have a value here of 2. Then we'll come back and get f of 4. Well, f of 4 is going to be those. That's going to give me it's going to give me a 3. And now I'm ready to calculate f of 5, because that's going to calculate, that's going to give me a 5. And then this is going to get filled in, and that's going to give me an 8. And that's going to give me a 13. So that's what's going to happen when I do the top-down approach. I'm going to try to calculate f of 13. I'm going to go down, but really I'm filling in a table. So why do that? Maybe I can go this way directly, right? In other words, let's say I just go to the definition, right? And then I just, instead of doing all this fancy recursion and calling things and filling the memo in, I just say, look, the definition of this is my 1 and this is my f of n, right? This is my n's and f of n. So that's a 1 and that's a 1. And then just then work the table this way, right? Instead of a top down doing the f of 7, I just go from the bottom up, right? I fill the table in. And so as I work my way up, what's f of 3? Every one of these, right? F of any n in here is going to be the sum of the previous two values, right? That's the definition. So that's going to give me a 2, and that's going to give me a 3, and that's going to give me a 5, and that's going to give me an 8. And that's going to give me a 13, right? So if we recognize that we have this this dynamic programming problem, sometimes not, but sometimes it's very easy to translate that problem. Instead of writing the recursion with a memo, just start with a table. Forget about the recursion and just iteratively fill in the table. So that's an interesting thing about this whole dynamic programming approach, right? It's much easier just to formulate the recursion and plug in the memo. It's not that easy to figure out in many cases what the bottom up approach is. But if you can do that, of course, it's going to be certainly faster than the recursion, even with the memoization, because there are no intermediate function calls, right? It's all done iteratively in filling in an array. Right? So, and we're going to come back to this later on, but this is a very, very important idea, right? This dynamic programming, and we'll see later on, we'll look at some other examples where this is extremely useful.